So that is why we spend a lot of time talk about impedance transformation, because it's very important, especially in this type of architecture. We can also look at BJT versions. There is slight difference in BJT cascode structure simply because of the introduction of RPi. BJT cascode structure for pulling down current source will be something like this: Q1, Q2, and then VB1, VB2. Okay? So we can also simulate this as to, this will be equivalent to a common base structure, Q2, RO1, right? And then we're also looking in for its output resistance. So you go back and check the equation. So I'm using a already simplified version. RL is approximately GM2 RO, because it's the second M2 transistor times RO1 in parallel RPi. And we know that in this case, RO2, so there's two scenarios. Let's just discuss that. So for RO2 to be a RO1, sorry, output resistance, much larger than RPi, what happened is that your overall R out would then be beta RO. Let me rewrite this. So this would then be GM2 RO2. Because RO1 is much larger, so you see RPi. And therefore, it will be GM RPi, therefore, is beta RO. Let me just say that for bipolar version, GM1 is always equals to GM2 equals to GM. Why? What is the GM of bipolar? You still remember? I should say approximately. Yes. For GM is ICQ, right? So it basically has, there's slight difference in current because emitter current and collector current are slightly different. But this is ICQ. So it's a single branch. There's a slight beta effect. But if you ignore the effect of beta, maybe less than 1%. So this branch, meaning that its collector current is almost the same. Because it's almost the same, so it should be almost identical in all cases. In MOSFET, it's harder for me to say that. It's because in MOSFET, you could use W over L to adjust so that not necessarily both of them has the same GM, even though their current can be the same. The current through a cascode structure, remember, I want to say it again. ID1 equals to ID2, equal to the same biasing current in this case. And this is also about the same. So in this case, IC1 is approximately equals to IC2. And it's a fixed current, fixed branch current, if you ignore the base current effect. So that is to say, because GMs are the same, and RO, because current is the same, this is because IC is the same, almost the same. That is to say, RO1 equals to RO2 equals to RO. You don't have any margin in adjusting RO because if you're using the same technology, it's the same early voltage. There's no adjustment. For previous case, of course, you can have different channel lengths. Therefore, its modulation effect can be different. But for BJT, basically, it's the same. OK? So GM1 equals, so you get this result. And this is typically the case because my early voltage or my this RO1 is much more larger than beta. That is typically true. OK? So what happened is that this would then lead to your overall output resistance. As I said, your would then be beta RO for BJT cascode. OK? So that will lead to a limitation as to how does one stack things up. So let me explain why. So if you talk about MOSFET and the difference between a MOSFET cascode current source and that of a BJT, one of the things is that if I'm not satisfied with this output resistance, what can I do next? I'm stacking 2. Can I stack 3? OK. So what happens if I stack 3 for the above solution? If you think about it, if I'm doing 2 versions, I'm just assuming they're having the same this is just I just want to give you a sense as to what are the limitations of these two. So if I'm looking in from this 3-stack structure, what happened is that I could actually, assuming that if I'm looking in from here, I already know this is GM RO squared. OK? So simply R out will be GMRO based on the same equation times another GMRO squared. Right? You amplify by whatever is the bottom resistance. This is RS. So this will give you GMRO squared times RO. So your output resistance is being boosted twice when you cascode 3 layers of transistors. So what happened to the BJT version? If you think about it, so this is the MOS version. Let's look at the BJT version of 3 stacks. Q1, Q2, Q3. OK? So if I'm looking down, I already know this answer. I already know that this will be beta RO. If you're looking down, it should be beta RO. So based on this equation, if I'm looking down from here, my RO should be GM RO. I'm just going to highlight 3 for now. Just make sure that you know that it's being amplified by the top transistor. And then following that, it will be RO R pi in parallel beta RO. OK? So what happened is that we know that if you compare R pi and beta RO, which one will dominate? Of course, R pi will be much, much smaller than beta RO. Therefore, the output resistance will then become GM RO R pi. Again, so it's beta R. So that is to say that you only need to stack once for bipolar, because if you stack more, it doesn't help. The reason why it doesn't help is because it's in parallel with R pi. So this R pi would then dominate whatever is being stacked up, so it will not be able to boost it one step further. Okay? So let's go through two examples for us to understand a design of a cascode amplifier. What are the limitations? So once again, if I'm doing this, okay. A cascode current source. So there's mainly two features you want to see in your current source. One is its output resistance. The other is, I actually didn't plot it here, is because you want to know its operation range. So basically, you want to know when it starts to become flat. For example, this is VD set. So we know that it only works when it's above a certain biasing level. So this is the SMU. The example of cascode, the concern R1 is R out. The other is its VO minimum or maximum. So it's basically its operation or operation range. So these are typically trade-offs, because when you actually doing cascode structure, you probably limit your operation range of being a high output resistance at the high output resistance range. So let's use an example of a pulling up version. So I'm using a PMOS. So let's say if this is my case, you need to find two parameters. One is its output resistance. One is VO maximum. If you're looking at pulling up version. So this is VDD. I'm having two transistors, well, M1 and M2. And this is VB2, VB1. So I'm looking up to the top for its output resistance. And I'm also checking where is my VO maximum. In this case, because it would then, you want to know, because it's looking up, so you want to know where your ceiling is. Okay? So this will then be equivalent to a current source. Okay? So let me give you parameters, and then we're going to design to find our output resistance and its biasing design. So example, let me give the parameters. Let's say threshold. We're going to ignore body effect here, because this one actually is subject to body effect as well. And lambda equals to 0.1 volts. And we want our I1 to be 100 microamp. And I'm setting my transconductance. These are given. This is given by design criterion, GM2 equals to 0.5 milliamp per volt. So these are the settings. So to achieve that target, we want you to first set VB1 and VB2 so that this is met. The other is to find its output resistance, of course. And lastly is to determine in that setting what is your ceiling, what is your maximum voltage, so that you're still operating, both transistors are still operating saturation. Okay? So first of all, anytime you have current and GM, the thing is that you allow us to set your overdrive. So you can use for part 8. Let me see where I'm going to move. Just give me a second. So let's start by determine its, we start part A. I'm just going to use this. So we know that GM can be expressed as, once again, we use this a lot, especially in design problems, because typically current is set by your target, and then you then have transconductance being set. So this is ID VGS minus VTH. That's my overdrive. So this would then give me, this is VOV. So we know that my overdrive will then be determined by ID divided by GM. Because the GMs are known, current is known. So that this is 0.2, and this is 0.5. This will give me 0.4 volt. In terms of setting up the overdrive for both transistors, we're using identical transistors for now. Assuming that M1 and M2 are identical, let's say W over L1 equals to W over L2. Okay? And then, so this would then tell us that what is the voltage between, you can set VB2 now. So VB2 should be VDD, that's minus I should say VSG2. And what is VSG? VSG is VDD minus a threshold of PMOS plus VOV. Just to be precise. It's a PMOS threshold because we're talking about PMOS transistors. Okay? So this will then give me, did I give the voltage? This is 1.8 volt. So this is 1.8 minus 0.5 plus 0.4. This will be 0.9. Okay? So this already tells me that this voltage set this bias to be 0.9 volt. Okay? So how does one determine this voltage, VB1? This one is already known, but this one, because this drain voltage or the drain voltage at this is undetermined, so it's set by your whatever you want. So typically you want to set it to the highest level, which is you want to set this point to the highest level so that this can be moved to the highest level. Therefore, typically, this is set to one threshold higher. So this, let's say Vx is set to VB2 plus one threshold, so that it will be at the edge, so that it will still be in saturation, at the edge of saturation. So it will be 1.3. There you get it, 1.4 volts, sorry. You want to set to 1.4 volts, so it will be at the edge. So M2, let me write it down clearly. You set it to 1.4 so that M2 is at the edge of saturation. So sort of like you want to push it to the boundary so that they will give you more leeway for setting this up. If you set this too low, this voltage will have to go lower. Therefore, this voltage has to go lower. So this is to maximize your operation region. So remember, this is set by VB1. So VB1, therefore, I can write it down. So VB1 will be Vx minus VSG1, which is VDD, the same thing, minus VTP plus VOV. So it's the same 0.9. So this will then set this to 0.5. OK? This will be 0.5 volt. So we already know where we want to set these two. So this would then, so if this is 0.5, what is your VO max? Meaning that M1 will remain in saturation. So VO max will then be VB1 plus a threshold, right? So this will be 0.9. So I'm already answered part C. OK? So this is when both of them are at the edge of saturation. What is the edge of saturation is this. What I mean by this is the edge of saturation. So this is saturation. This is linear. I should say at the edge of linear it's the same, but because you're coming in from saturation, so this is the edge of saturation. Before it enters linear. So you don't want it to enter linear, otherwise all the model doesn't work. Your small signal model doesn't work. All the equation doesn't work. So lastly, we need to find out its output resistance. So its output resistance, we're going to follow its equation. So the equation is fairly simple. For part B, R out was simply GM 2 RO2 times RO. So what we need to do is to find, we already know GM is 0.5 milliamp per volt. We know that RO, there's only one RO, they're the same because they're the same current, lambda ID. So this is 100K. So once we have these numbers, we can find out that GMRO equals to 50. Get it right? Therefore, your R out is 5 megavolts. OK? So you want to see that this is a very powerful tool to get large resistance. Because if you think about it, I've said it many times, is that it's actually very hard to construct resistance, especially to get large resistance in integrated circuit. So you typically wanted to use transistors characteristic to effectively give you this current source-like or high resistance-like behavior. So by stacking 2 transistors, much area, more area sufficient. You could think, if I give you some, if you ever did any tape-out examples, if I give you a resistor model file, for example, you will see that to create such resistors, 5 megaohm resistors is essentially impossible, or it's very, very area consuming. You use like a snake-like, routing to get very, very large resistance. You need a lot of routing area in order for that to be realized. So this is a very powerful tool for this to be realized. So, so if we look at current source behavior, as I said, there's 2 key parameters. There's always trade-offs. So if I ask you to draw the characteristic of this current source, so this is equivalent to a current source. You want to draw I1 as a function of VO. This is the current source. Okay, so let's say this is VDD. So there's a limitation as to where it can go, because it's a PMOS, so it goes the opposite direction. As I said, it has an upper limit, VO maximum. So only when it's within this, from 0 to 0.9, so it's about half. So this is 1.8. In scale, you will see that this is 0.9. This is where you get RL 5 megaohm, meaning very, very high. It's fairly flat because it's a very high resistance. Right? When it enters transition, so this is the region where both M1 and M2 in saturation. When you start to enter higher voltage above 0.9 volt, then either one of the transistors will become a linear, so you get degradation of its slope, and then it will look something like this. So you first get sort of degradation in its slope, and then it will go like that. So your operation region is fairly limited. This is VO minimum. This is your VO max. As I said, it's being set by VB2. Okay? So I want to emphasize once again the benefit of having a cascode is to have high output resistance. But the main trade-off is that it will lead to much lower operation. The analogy I would like to use is that a cascode structure for amplifier or even for having current source is like wearing a lot of clothes to isolate yourself from heat. So what happened from cold? But what happened is that when you wear a lot of clothes, it's very hard to move. So it limits your movement a lot because of this isolation. Anytime you do isolation, the cost is your freedom to move. Okay? So that will be the same when we add amplifier. So when you add amplifier, then that will cost the same thing. Okay? So we're going to stop right here, and then I'm going to hand out exam questions, exam sheets, sorry. 我们要发考卷。Okay, let's start today's discussion. Before we start the actual discussion, continued discussion on Cascode and current mirrors, I would like to make a few announcements. First of all, if you have any concern with your grades, please make an appointment with me. There is room for adjustment. You have to do it beforehand. So if you have any concern, after midterm has been handed out, you have concern with your final grades, please come by for some discussion. And the other thing is that we will have our fourth quiz. Every time I would like to align with you as to what needs to be completed at this particular moment. So we still have 3 more quizzes, therefore it's 4, 5, 6. And quiz number 4 will be held this Thursday, and it will cover mostly MOSFET devices, which will be mostly device physics, some single choice questions, and then a calculation questions based on a common source stage. And then you need to know how to analyze, for example, the DC bias analysis and some small signal analysis, basically. So you need to bring a calculator. I'm going to make the announcements now. So make sure that you bring your calculator for quiz on Thursday. And then some students asked me what will be covered in the final. So basically, we have 3 more quizzes, a final exam, and 2 more homeworks. So make sure that you know what needs to be done in completing this course. So final will start covering whatever not covered by midterm. So it's chapter 6, 7, which is MOSFET and single-stage MOSFET, single-stage MOS amplifiers. And then we're going to talk about chapter 9, 10, 11, so which will be differential cascode and current mirror, differential pair, and frequency response. Okay, so these are the material you're supposed to be familiar with yourself for the final exam. So these are the things that we need to hit at the end of this course. Okay, so any questions? Yeah, I would like to give the lecture without mask, therefore, just to keep a safe space. Okay? So if you have any concerns. So we have already started a little bit on the discussion of cascode structure. As we have already discussed, the stacking of stages allow us to have a better isolation from the output node to the ground, basically. What happened is that it can be used for 2 purposes. One is for current source to provide a more ideal current source. And of course, it can also be an amplifier. So it can be a voltage amplifier, for example, input, output. So we're going to talk about these 2. We're going to review a little bit on our discussion on using the structure as a current source. And then we're going to talk about how does one analyze when we have two transistors stacked together. How does one analyze what we call a cascode amplifier? And what is the pros and cons of using this type of structures? And then lastly, for chapter 9, we're going to talk about current mirror. This is a very, very important type of structure, which is very commonly used. We're going to talk about this especially this is used in an integrated circuit. Integrated circuit because it has compact devices. Therefore, doing sort of the mirroring design. As we're going to talk about differential pair, these are things that because of the development of integrated circuit, therefore these structures become viable or make sense in order to make these type of structures. So it's mostly used in integrated circuits. You don't actually see this too much in discrete components. In discrete circuits, you do resistor biasing. But for integrated circuits, then we can use these type of system to do biasing system for multiple stages. Let's just say you don't have to dig your own water tank. We have a reservoir. We have a water system which will then allow us to pipe the water to every household. That's what it is for current mirror system, which allow you to have one single reference, and that can be multiplied to multiple stages. So we're going to talk about that a little bit in this chapter as well. Okay, so let's review a little bit on what we have already discussed on using a cascode structure as current source. For realizing current source. I believe I used an example last time as a sourcing current source. You can also do the same thing for sinking current source. So basically what we look for in a current source, I'm just going to do both MOSFET. So I'm assuming I'm using this type of structure to construct my, that is Q1, Q2, M1, M2. So if I give fixed bias, just to follow convention, so this will then allow us to construct, this will be equivalent to a current source, right? A sinking current source with a set current that's being, the current level is being set by biasing condition. So the DC level is set by VB1, VB2. Through this setting of biasing condition, you should be able to determine your DC biasing condition. Okay? So what we actually look for in terms of characterizing a current source is that what are the key, every time you talk about analyzing a circuit, you need to understand what are the key parameters you're concerned about, what are the key components we think that it's important to describe a current source. As we said, it's basically two parameters. This is the same as input-output resistance and voltage gain if you're describing a voltage amplifier. But current source, of course, there's also benchmark allow us to evaluate whether it's a good design or bad design. So as I said, for current source, what you want is I versus V. If I'm looking at current, IO versus VO. So basically what you want is that you want to make sure that it's at the level, this is the ideal case, which is the level that I set and it meets the level, right? So this is the ideal. So we're going to look at what happens if you're using a cascode current source. It basically has two limitations. One is that it will then have a finite line, which means that it's not a flat line. Let me highlight this, the slope equals to 0. Right? So it has, as I said, resistance infinite. Indicate that if it's a flat line, meaning that your output resistance is infinite, which by definition of current source, meaning that its current does not change with bias condition. It's supposed to give you 1 milliamp no matter what, right? But for the real case, you would then have something with a finite RL. So this is something that we want to do. The slope is 1 over RL, right? The slope is 1 over RL. So if it's not a flat line, you would then have a finite output resistance. And then the other thing is that when does this reach this high flat region? Just to be precise. So it's supposed to reach the level by design, and then there's a slight increase. So the inverse of the slope is RL, depending on where you want to express it. So the other thing is that it has a, we call the VL minimum. So above this, this can be served. This is the operation region. Viable operation region. Below that, it will then does not have a flat response. And the current level doesn't meet the target level. So it's very close. So precision and output, so there's two parameters. One is this RL, output resistance. The other is output, VO minimum. So if I give you this circuit, you should be able to determine what is these two key parameters. So first of all, you want to look at what is RL on the left-hand side. So for the case on the left, which is a MOSFET. So in both cases, I'm going to assume GMRO. For both cases, much, much larger than 1. These are, by default, mostly true. So for RO for BJT, remember, is GM RO times R pi. The resistance you see over here, downwards. So there's two. One is this, R pi. The other, sorry. This is R pi, and this is RO. Okay? So if I'm looking down from here, at this particular point, there's two resistance in parallel. So you can simply say that as this. And then it's approximately, because R pi is much, much larger than, smaller than RO, therefore it's approximately GM R pi RO, therefore it's beta RO. Okay? So this is what happened for the BJT version for the circuit number 1. Let's look for the MOSFET version. So MOSFET, you also look at this terminal. At this source terminal, there's only one resistance, right, RO. So basically, you follow the same equation. So for circuit number 2, for MOSFET, this is MOSFET version, which is, I would say, I'm just going to use it approximately. This is approximately GM. There's always GMRO times whatever you see downwards. So which is RO. So you get GM RO squared. Okay? So this probably order of magnitude is correct. So the main reason you see this is because there's only one. Okay? And then we want to determine, so each one of the circuit has two key parameters. One is the slope. The other is what is the operation region for this circuit. So for this circuit, you only need to see what is the minimum point at this terminal. Right? This is VO minimum. This is VO. This is output voltage. What is the output minimum? For MOSFET, we already know that it's determined by whether this M2 is in saturation. Therefore, is VB minus a threshold voltage. Right? This is just to set at the edge of saturation for M2. Right? So this is because when it goes down further, M2 will then enter linear region. So at the edge of saturation will be this voltage. So this is VO minimum. I should be clear on this. So its operation range is another important thing. Yes? Yes, VB2, sorry. It's supposed to be VB2. Yes, correct. It's VB2. Thank you. So for MOSFET, for BJT version, this is the same thing. We know that for this BC junction to be remain in saturation, this BC junction should be 4 bias less than 0.4 volt. So for this case, you would then have VB2. So VO minimum for BJT will then be VB2 minus 0.4 volt. So this is BC4 junction, this VBC. So VBC needs to be less than 0.4. This is at the edge this is limited by Q2, edge of active. You want Q2 to remain active, so where's the boundaries when this is lower than this? This is start to 4 biasing by less than 0.4. More than that, you would then suppress Q2. So Q2 is the first one. If you're doing the circuit, this type of circuit, Q2 is, or M2 is the first one, which will then go out of the operation region. For example, out of saturation or out of active region. Okay? So this is, these are the two basic parameters. If I give you a question, analysis question or design questions on cascode structure, cascode current source, these are the two index. You need to know how to analyze it or how to determine what its level is. Okay? So the next thing we're going to move on is that we could also use cascode structure as an amplifier. So let's look at how it works as an amplifier. In this type of structure, I'm just going to use an ideal current source just to make our life easier, and then we go back and put in cascode current source. So as I said, cascode can also allow us to deliver a good or a high gain. We can say that it's a relatively high gain amplifier. So I'm going to use a BJT version as an example. So first we look at a BJT cascode. So just to focus our analysis on the amplifier itself, I'm going to use an ideal current source, I1. So I'm just assuming that if I have an ideal current source as the biasing component. So let's look at how this cascode structure enables us to have relatively high gain. So instead of having a fixed bias as compared to this current source, what happens is that I would then have one terminal, the base terminal, input, and your output terminal here. So if you look at the signal path, what happens is that your input coming in from base, and then it's being amplified. So this is a common emitter stage, right? So this will then be my VO1 equals to V in 2. So if you think about it, this is V in 1, just to be precise. VO2. Let me just use convention. So this will be V in 2, and then this will then. So you have a common emitter at the bottom, and then I have a common base as the next stage. So you can look at it as a two-stage amplifier. One stage, even though we typically call it single stage because one biasing is typically refers as single stage, but you can look at it as a CE plus. So it's essentially a common emitter plus a common base. Okay? So how does one analyze its voltage gain, its input-output resistance voltage gain? Because you want to deal it with an amplifier, so you want to look at its Rn. Of course, 3 key parameters, voltage gain. So how does one calculate these parameters, or how does one obtain these parameters? So first of all, we look at input resistance because you're looking in from here. This is fairly simple. And there's various ways of doing this. You can simply just draw the small signal equivalent circuit of these two circuits and then do the small signal analysis. But I would like to do it in two ways. One is to treat it as two stages, using two stages. The common source, we already know the two-pole model for CE and CB. That's one way of doing this. And then I would like to also do another analysis to look at the circuit more like a transconductance amplifier. It's actually much easier. So we're going to look at one way is to use two-stage analysis. So I'm not going to use the small signal. You can use the small signal model, just stuck it in and then do the small signal equivalent circuit. It should give you the same answer, okay? So I'm going to do the two-stage analysis because we already spent a lot of time develop our two-pole model. So look at the common emitter. So if I'm using a two-pole model, I'm having two stages, right? So I have Rn1. Let me highlight. And then I have R out 1. So this is my, AV1, V1. I'm going to treat it as two stages stacking together. So this part, this will be my common emitter stage. And because this output, remember my input is coming in. This is V in 1. My overall gain should be VO2 versus V in 1, right? So this is VO1. Equals to V in 2. VO1 as V in 2, and it's connected to the next stage. I'm just going to use the two-pole model continue. So for the two-pole model, it will be R in 2 and AV2, V2. V2 is this. Right? And it's connected to RL2. Okay? So I'm just going to give you all the parameters based on our previous analysis or understanding of these type of circuits. So for let me highlight. This is the common base. Okay. So my Rn for the first one, we already know this is R pi 1. Right, because it's looking down, there's an R pi. Right? And your voltage gain in this case is GM. And then because it's GM times whatever is at this particular location, so it's GM times its output resistance, I should say the resistance you look at this particular node. But if you're looking in from this node, we know that this GM is actually, I should say, let me think about how I'm going to phrase this. This is, let's assume that we're opening circuit by this. So this will be RO1, GM1 RO1. Okay. So your RL1, this is RL1. Because you're looking down, you're assuming you're open circuit. This is assuming open circuit, so you're looking down. Here's this RL1. Okay? So if you're looking in from here, remember we're seeing 1 over GM. GM2. And then your voltage gain is actually GM. RL. GM2RL. I should say GM2R out. Because we're only looking downwards when it's open circuit. So if I'm multiplying this in together, I'm using the same equation. So your output, VO, just to be VO2. So if I'm writing down VO2 as a function of V in, that's what eventually what we want to get to. So VO2 will then be AV2, V2. And what is AV2? AV2, we already know that it's GM2 times its output resistance. When output resistance is this, right? When you're using a cascode structure. And then times V2. So V2 is a voltage divider, which is AV1. So there should be a minus sign in front. I'm losing this minus. And I have, what is V2 is the voltage divider. So it's R in 2 plus R out. R in 2. Okay? Yeah, R in 2, yeah, correct. So you're basically losing the gain from single stage out of this. And then this will be V1. And we know that V1 is, this is just V in 1. It's the same. So your overall gain, the overall gain of the cascode stage, this is the overall cascode amplifier gain, should be V in 1, VO2. That's your overall gain. You're looking at your output going back to input. So this will be GM2, RO2. And this is GM1, RO1 times sign. I'm having two V1s. So V1 is V in 1, right? And then it looks complicated, but we'll simplify it pretty soon. There's a minus sign because of inverting amplifier of common emitter. And then finally, this is RO2, 1 over GM, 2, 1 over GM. Okay, this is just to be precise, but one of the things I want to highlight is because this is a single branch current, so we know that GM1 equals to GM2 equals to, because the same I1, which is I1 divided by VT. So this equals to GM. For bipolar, there's no room. There's only one GM because we're having a single branch. There's a little beta correction. I'm going to ignore that. Just assume beta is larger than 1. Okay? And RO is the same. RO is I1, a VA divided by I1, so that RO1 equals to RO2. So no need to label them differently because single branch, you can assume that the output resistance and transconductance are identical. Okay? So after some manipulation, you will see that it will be approximately, so this will be GM, and there's another minus GM squared RO, where's RO1? I should. So this 1 GM, there's 2 GM, and this is 1. You could simply time the GM. Let me write it down. So there will be GM squared R out 1 RO times, let me think, 1 plus GM RO plus. Okay? So you simply ignore that, and it will get rid of one of this. It looks a little complicated, but whatever we're going to do, eventually what you get is minus GM. I should say this is RO2. Okay? So what is RO2 eventually? Remember, when we have a cascode structure, your output is being boosted RO2. You're looking back into here. This is the same equivalent circuit. You're looking back from here. So we're using this equation, which is RO2 is simply beta RO. So overall, we're going to get a voltage gain of minus GM beta, or you can rewrite it as beta GM. So it's an intrinsic gain and amplified by a factor of beta. Okay? So this is just an exercise allow you to use your already developed two-pole model, continue to develop into cascode and into a cascode analysis, and then we get the overall gain. Yes? 那我看一下哈，哪一个？这边吗？红色。Oh, this is RO1, sorry. This is RO1. The voltage divider is RO1. You're right. But it doesn't really matter because RO1 and 2 is the same, eventually. So you the simplified results will be something like this. Okay? So this is when you use a two-pole model to analyze this type of circuit. Another way of looking at this is to look at the circuit as a transconductance amplifier. As I said, for transconductance amplifier, so this is use two-stage analysis. You can do transconductance It's actually a little bit easier if you use transconductance model. The way to think about it is that if I'm looking at a cascode structure, something like this. Common emitter, common base, V in, yeah. The way to use transconductance model is that I'm going to describe something called GM. GMS. GMS, S stands for short. So when you short output, what is the maximum current? So it's basic, for transconductance amplifier, what you look for, this is VL. And then we look for this current, we call this current. Right. You also look for output current. So by definition, this is I out as a function of V in when output, when this is short. So this is when V out equals to 0. That stands for output short, where you get the maximum current. Okay? So what is your output current? If you think about it, what is the small signal output current? Is actually this current. So it's, if you think about it, I'm just going to do it in a more hand-waving analysis. So IL is actually collector current of Q2. So this is Q2, Q1, right? So I'm just simply going to write IL equals to IC2. So IC2 actually can be related to IC1. This is IC1 by a factor of, so IC1, the relationship between IC1 and IC2 is a, because remember, common base stage is a current buffer. If you think about it, its current gain is close to 1. So the ratio between the two is IC2, I should say, let me write it this way, is 1 plus beta beta IE2, right? IC2 equals to, they have a different color. Let me write it down. This is actually IE2. This is emitter current of Q2. So I can rewrite this because I connect emitter and base, therefore IC2, this is IC1, right? Because this equals, the emitter current of common base equals to the collector current of the first stage. And then this is approximately 1. So I'm just going to use, so what is this? IC1 is modulated by this. So IC1 is simply GM minus GM V in, V in. Right? So I already know that by this stage, you simply have a GM, it's simply GM1. It's the same. And equals to GM. So the way to think about this is that anytime you modulate the emitter base current, you modulate, you get a GM out of IC1, and this IC1 propagates to IC2 through a current buffer with a gain of close to 1. Current gain close to 1. Okay? So once I have this, then my remember a two-pole model of transconductance two-pole model, then look for output resistance. Output resistance is the same. It's the same as the left one. So R out is simply beta RO. Right? So your overall voltage gain will then be GM as times RL. This is equivalent. This is just a Norton Thevenin equivalent. Therefore, your voltage gain is the same as transconductance times output resistance. This will give me minus GM times beta RL. So your overall gain will still be the same, beta GM RL. Okay? So this is actually much easier if you can look at it. Look at the circuit as a transconductance amplifier, meaning that you transduce the current through IC1. The modulated current is being amplified by GM in, and this being transferred into the output terminal through this current source, current buffer with a gain of approximately 1. Okay? So we can simply use this to analyze our MOSFET counterpart. So we can do the MOS cascode amplifier. It will be actually much easier because we don't need to consider beta at all, because source current equals to drain current. So for a cascode, the amplifier is the same, I1, VDD, and then it's it's a MOSFET. So we do the MOSFET counterpart. Okay? So this would then be M1, M2, my impedance is still at gate. My output is here. Okay? I forgot to do a summary on the left, on the bipolar circuit. So for bipolar cascode circuit based on that structure, I have Rn equals to R pi voltage gain equals to minus beta GMR. And then my output resistance is very high, is minus beta R. So this one. Okay, so that's the summary for the cascode amplifier. We look for 3 key parameters. We're going to do the same for cascode MOSFET amplifier. It's the same. It has, as I said, based on this, you have, this is a common source stage. This is the common gate stage. You have a common source stacked with a common gate. Okay? So we're going to do the same thing for MOSFET version. We know that Rn, there's no discussion because it's coming in from gate. So input resistance is infinite. So we already answered one part of the question. I'm going to make our life easier, just assume that the transistor, the biasing current is the same. We're assuming that W over L 1 equals to W over L2, just to make it easier. Therefore, your transconductance is the same. So GM, this simply implies that GM1 equals to GM2 equals to GM. And RO is the same. You can actually include this. There'll be minor difference, but the eventual results will be the same. If you include both of them, it doesn't really make too much difference. I should say, if 2 devices has different RO and GM, it will be the sum of all. Okay? Okay, let me. So the way to think about this is the same. If you want to look at this particular point. So I'm not going to do the complete 2-point model, just a more simple way of looking at this. If you're looking at the intermediate point, which is labeled as VO1, so your VO1, based on our VO1, if you're analyzing this circuit, it should be minus GM1. And then I'm looking at this particular point. What is the resistance at this particular point? So at this source terminal, you will see RO1, and then you actually see from the top, you will see 1 over GM2, right? So it's the transconductance times the overall resistance. That's the basic output voltage. So your output voltage is transconductance times the modulated current, I should say. It's GM1 V in. So that's, I should say, that's delta ID. It's the modulated current times its resistance. Its resistance is 2 RO1 in parallel 1 over GM2. So if you're looking down, is RO1, looking up is 1 over GM2. So then, what is VL? So this is the intermediate point. And then you actually won't see the effect of this. And then this will be minus GM1. Right, this will be approximately the ratio between two GMs. And if GM is the same, meaning that your, sorry. Let me write it downwards so that it won't confuse you. So this will be approximately GM1, GM2 times Vn. Okay? So you actually see that one of the key points, this has some implication for you to get, is that because of this particular structure, what happened is that you actually, because of this low input resistance of the common gate stage, it will actually, you will not see amplification of voltage at this particular point, meaning that the voltage is actually the same. The magnitude of the voltage is almost the same. It's almost the same, identical if I have the same GM, meaning that it does not do voltage amplification across these two terminals. This is also have some implication when we analyze frequency response. So it's one of the key. We're going to talk about it later. That's especially beneficial for some sort of to eliminate a capacitive amplification effect. So when you're not amplifying this terminal is somewhat important in subsequent analysis. Okay? So you get this particular point, and then this is being amplified. So this is a common gate stage. I know that my output should be, based on common gate stage, supposed to be GM. GM2 R out times VO1. So this is the second stage if you consider, this is when we consider the common gate stage. The previous equation is when we consider the common source stage. So I'm just going to substitute this into here. You get GM2 minus GM2, GM1, Vn, right, times R out. So the overall gain is VL, Vn, and the GM2 cancel each other, so it's minus you see something familiar. It's the same as our previous transconductance analysis. It's the transconductance of the first stage times the overall output resistance of the cascode stage. So we know that R out equals to, go back and check using this equation, which is GM2. I'm just going to be just to be precise, it's GM2 RO2 times RO1. Okay, so if I'm flipping this back into this common gate stage, it will be minus GM1 RO1 GM2 RO2. So it will be the intrinsic gain of both stages stacked together. And because in most cases, if you're designing your transistor identical, it will simply be GMRO squared, the minus remains. So that's how we get why this is typically referred to as a high gain single stage amplifier. Using a single stage, you can get the intrinsic gain of two stages. Okay? So let me write this down. So we already know that our voltage gain is minus GM RO squared. And then finally, R out is minus GM RO